Hello everyone. In this video, I will explain what floating point format is. I will demonstrate how to convert a decimal number into floating point. I will demonstrate how to convert a floating point number back into decimal. I will show how to use the provided Python program to solve any floating point conversion problem. And finally, I will show how to use the floating point IP course. So, what is floating point format? Well, floating point format is used to represent real numbers in binary. The two main IEEE 754 floating point formats are single precision and double precision. In both cases, the number is divided into three fields: assign bit, exponent bits, and mantissa bits. The table below shows how many bits are assigned to each field in each format. The decimal equivalent of any floating point number can be calculated using the formula below, where S is the sign bit, E is the exponent, and M is the mantissa. The constant B is 127 for single precision and is 1023 for double precision. When given a floating point number, you can determine its decimal value by using the 4 steps below. So now let's do an example where we convert the following single precision floating point number into decimal. The first step is to find bits corresponding to S, E, and M. We must first convert from hexadecimal to binary. After converting to binary, we use the most significant bit for S, the next 8 bits for E, and the remaining 23 bits for M. The second step is to convert E to decimal by treating it as an unsigned binary number. So this is the original binary value of E. Each bit of E with its corresponding index and contribution are shown in the table. E is the sum of the contributions from all bits equal to 1. E is finally determined to be 129. The third step is to convert 1.m into decimal by treating it as an unsigned binary number. So this is the original binary value of m. Then this is the value of 1.m. Each bit of 1.m with its corresponding index and contribution are shown in the table. 1.m is the sum of contributions from all bits equal to 1. 1.m is finally determined to be 1.4375. The final step is to just plug in the values into the formula. After doing this, we get our final answer. You can convert any decimal number into its floating point form by using the 4 steps below. Let's now do an example where we convert the decimal number -82.875 into a single precision floating point number. So the first step is to convert the absolute value of the number into its unsigned binary form. The second step is to shift the decimal point until it is after the most significant one. If shifted left by n, multiply by 2 to the power of n. If shifted right by n, multiply by 2 to the negative power of n. Our result from step 1 needed the decimal point to be shifted left 6 times. Since we shifted left by 6, we must multiply it by 2 to the power of 6. Finally, we save the value of n for step 3. Step 3 is to obtain S, E, and M. Since -82.875 is negative, S is equal to 1. Then we calculate the value of E and convert it into binary. M will be all of the bits after the decimal point. We must also zero pad M to make it be the right length. The final step is to simply reformat the answer. To do this, we must concatenate S, E, and M, reformat to make hex conversion easier, and finally convert to hex. Once we have done all of that, we finally will have our answer. IEEE 754 also includes special cases that cannot be evaluated using the main floating point formula. These special cases are 0, infinity, nan, and subnormal numbers. 0, infinity, and nan require no calculation because they can be identified using predefined bit patterns. Subnormal numbers, on the other hand, require a separate formula and will not be covered in this lesson. A floating point number is subnormal whenever e is all zeros and m is non-zero. A decimal number x is subnormal whenever it falls into the following range. The project files also include some basic IP blocks for adding and multiplying floating point numbers. These blocks are purely combinational, so you just provide the two floating point inputs A and B, and the output C is calculated automatically. Alright, so if you did not realize it already, all of the floating point rules are deterministic, meaning that the conversion process always stays the same. That means you can write a Python program that lets you solve any conversion problem and that shows the work too. This here is a demonstration of that exact program in action. So I'm going to convert the number -523.25 from decimal into single precision floating point. As you can clearly see, the program automated the entire thing and showed the work too. So let's do one more example. Now let's convert the single precision number 83CA0000 from single precision floating point into decimal. As you can clearly see, the program automated the entire thing and showed the work too. This program is included in the project files, so whenever you need to convert or interpret a floating point value, you can quickly use it to obtain the answer and verify each step. Now let me demonstrate the provided IP cores. This is the floating point adder included in the project files. As you can see, the project already contains the source file and a completed test bench. After running the simulation, we can change the waveform radix to double precision floating point. Once we do that, we can clearly see that each addition was performed correctly. If you have made it this far into the video, you should now feel confident in your ability to interpret floating point values, convert between floating point and decimal, and use a provided IP core to perform floating point addition. Alright, that's all for this video, and I look forward to seeing you in the next one.